Imagine you run a company. You need AI, a lot of it. To train one model, you currently need an entire warehouse full of the most advanced chips on the planet. Those chips cost billions of dollars, and even then, you're still waiting. Now imagine someone walks in and says, "We can do the same job with 1/4 the chips, cut your cost per AI output by 90%, and your model finishes 10 times faster." You'd think they were lying, but that's not a hypothetical. That's what NVIDIA just told every major company on Earth. And the proof isn't a lab demo or a press release promise. The chips are already in production. The biggest cloud providers in the world are already in line. And the entire computing industry, from Intel to AMD to Qualcomm, already knows it. Their stock prices on the day of the announcement made sure of that. This is the story of two chips that NVIDIA unveiled in 2026. One is designed to reshape how the world's most powerful AI gets built. The other is designed to put an AI supercomputer on your desk or in your laptop bag. Together, they represent the most aggressive single-year move NVIDIA has ever made. And by the end of this video, you'll understand exactly why every tech company on the planet is paying attention. Segment 1. The company that now runs the world's AI. To understand why NVIDIA's announcement landed like a bomb, you need to understand the position the company is already in. For most of its history, NVIDIA was known for one thing: making GPUs for video games. Good business, solid company, totally unremarkable from the outside. Then AI happened. It turned out that the same chips that made video games look beautiful, chips designed to do millions of simple math calculations in parallel, were also perfect for training and running AI models. NVIDIA didn't invent that insight, but it moved faster than anyone to capitalize on it, building out the software and the hardware ecosystem that became the default tool for anyone building serious AI. The results speak for themselves. For their most recent full fiscal year, NVIDIA reported revenue of more than $215 billion, up 65% year over year. Their data center business alone, the division that sells AI chips and systems to hyperscalers and enterprise customers, brought in nearly $194 billion. That's roughly 90% of the entire company, all from AI infrastructure. Their market cap has crossed $5 trillion, making NVIDIA the most valuable company on Earth. And yet, somehow, the company just announced the biggest product leap in its history. Segment 2. Meet Vera Rubin, the data center monster. The centerpiece of NVIDIA's 2026 push is called the Vera Rubin platform. The name follows NVIDIA's tradition of naming chip generations after pioneering scientists. Vera Florence Cooper Rubin was an American astronomer who, in the 1970s, provided some of the first hard evidence for the existence of dark matter by studying how galaxies rotate. Her work changed what we thought we knew about the composition of the universe. Jensen Huang, NVIDIA's CEO, has a gift for this kind of naming. And the choice of Rubin is pointed because what she discovered fundamentally rewrote the map of physics. The implication is that this chip platform rewrites the map of computing. Vera Rubin isn't a single chip. It's a platform. 7 purpose-built pieces of silicon, all designed together, all meant to function as a single unified AI supercomputer when assembled into a rack. The chips include the flagship Rubin GPU, an all-new in-house CPU called Vera, a 6th generation NVLink interconnect switch, high-performance network cards, a data processing unit, and Ethernet switching infrastructure. Every one of those components was co-designed specifically to work with every other one, which NVIDIA describes as extreme code sign. The idea being that you can't get the best performance out of any individual piece unless the entire system is built as a whole. Let's talk about the Rubin GPU itself, because the specifications are genuinely staggering. The chip is built on TSMC's 3-nanometer manufacturing process, which is the most advanced semiconductor manufacturing currently available. It packs 336 billion transistors into a dual die design, a chip so complex that it literally couldn't be made as a single piece of silicon. It's 2 massive chips fused together. For comparison, NVIDIA's previous Blackwell GPU had about 208 billion transistors. Rubin is a 60% increase in raw transistor density in a single generation. Memory matters in AI, maybe more than anything else. The Rubin GPU uses HBM4, the newest generation of high bandwidth memory, delivering up to 22 terabytes per second of memory bandwidth per chip. The previous Blackwell generation managed around 8 terabytes per second. Rubin is nearly 3 times faster, just in memory access alone. And it does this not through software tricks or compression, but through raw silicon engineering. The performance numbers. NVIDIA is claiming at the rack level are the ones that really tell the story. The flagship configuration, called the Vera Rubin NVL72, packs 72 Rubin GPUs and 36 Vera CPUs into a single liquid-cooled rack. At full power, that rack delivers 3.6 exaflops of AI inference compute. NVIDIA's previous Blackwell NVL72 delivered roughly 700 petaflops. That's a 5-to-1 jump in performance in a single product generation. Segment 3, the number that will reshape the entire AI industry. But raw performance isn't actually the most important number here. The number that every CEO, every CTO, and every AI research director in the world circled when they read NVIDIA's announcement was a different one, 10 times lower cost per token. Let me explain what that means. When a company runs an AI model, say a large language model that answers customer questions or a reasoning system that helps doctors review medical records, the cost of doing that isn't just the upfront price of the hardware. The ongoing cost is measured in tokens, the small chunks of text the AI processes and generates, every single AI-powered interaction, every search query, every automated summary, every generated response, all of it is measured in tokens. For a company running AI at scale, the cost per million tokens is one of the most important financial metrics in their entire operation. NVIDIA is claiming that Vera Rubin delivers 1/10 the cost per million tokens compared to its own Blackwell platform for agentic AI workloads. That's not a marginal improvement. A 10 times reduction in the ongoing cost of running AI doesn't just make existing use cases cheaper, it makes entirely new categories of AI applications economically viable that were completely off the table at previous price points. Use cases that were too expensive to run at scale at Blackwell costs might work perfectly at Rubin costs. The market doesn't just get cheaper, it gets bigger. This is why you saw Microsoft announce plans to deploy hundreds of thousands of Vera Rubin superchips across its new AI superfactory sites. It's why AWS, Google Cloud, and Oracle Cloud all lined up as launch partners. It's why AI labs from Anthropic to OpenAI to Meta to xAI confirmed they'll be training and running inference on Vera Rubin systems. And it's why the Blackwell backlog, already sold out through mid-2026 with millions of units on order, is already in the process of being superseded by demand for what comes next. Segment 4, the Vera CPU, NVIDIA's big swing into CPU territory. Here's the part of Vera Rubin that has the deepest long-term implications and got the least attention in most of the coverage, the Vera CPU. NVIDIA has shipped CPUs before, most notably its Grace processor. But the Vera CPU is different in kind, not just degree. It's the first time NVIDIA has designed a standalone CPU specifically intended to compete head-to-head with Intel Xeon and AMD EPYC, the chips that have powered the world's data centers for the better part of 20 years. Why does a GPU company need its own CPU? The answer is in how AI workloads have changed. Training a large AI model is mostly a GPU job. You need to do enormous amounts of parallel matrix math, and GPUs are the perfect tool for it. But running AI in the real world, especially in the era of agentic AI, where models are taking sequences of actions, calling external tools, checking their own work, and managing multiple tasks simultaneously, requires huge amounts of general-purpose compute to orchestrate everything. Every time an AI agent decides what to do next, coordinates between subtasks, retrieves information, or evaluates its own output, that's CPU work. And as Jensen Huang put it at the Computex 2026 keynote, CPUs have become the bottleneck in the AI factory. The Vera CPU has 88 ARM-based cores, built specifically to handle the orchestration and reasoning workloads that sit alongside the Rubin GPU's raw computation. Early customers for Vera include Anthropic, OpenAI, SpaceX's xAI, Dell, Oracle, and CoreWeave, not as a curiosity or a supplementary purchase, but as what Huang described as NVIDIA's new major growth driver. Intel and AMD have each spent decades building the architectures that dominate data center compute. NVIDIA is now competing in that space directly, with a chip designed ground up for the AI era. That is not a small strategic move. Segment 5, RTX Spark, the AI supercomputer for your laptop. Now let's switch entirely from the stratosphere of hyperscale data centers to something much closer to home, your personal computer. At the Computex 2026 conference in Taipei in early June, Jensen Huang walked on stage and announced something nobody in the PC industry had been fully prepared for. NVIDIA is entering the personal computer chip market with a chip called RTX Spark, also referred to internally as the N1X. For most of its existence, NVIDIA made add-in graphics cards, chips that plugged into someone else's computer. The CPU inside the machine, the main processor that ran everything, came from Intel or AMD. That was the division of labor that defined the PC industry for decades. RTX Spark blows that model up entirely. The chip combines a custom ARM-based CPU with a Blackwell GPU onto a single piece of silicon, unified by NVLink, NVIDIA's high-speed interconnect, with 128 gigabytes of shared memory that both the CPU and GPU can access simultaneously. Think of it as taking a server-class CPU and a high-end dedicated GPU, fusing them together so they share the same memory pool, and packing the result into a chip thin enough to go inside a laptop. The The specs tell a remarkable story. RTX Spark delivers up to 20 ARM CPU cores, 6,144 CUDA cores on the GPU side, and up to 300 gigabytes per second of memory bandwidth. It can run 120 billion parameter AI models locally. The kind of model that, until recently, required a data center rack to run at all, with context windows stretching to 1 million tokens. Locally, on a laptop, without touching a cloud server. And it's not just AI performance. The chip also handles video. It can decode and edit 12K video, plays modern games at 1440p resolution and over 100 frames per second with ray tracing enabled, and renders three-dimensional scenes up to 90 gigabytes in size. RTX Spark is being positioned not as a trade-off between AI capability and traditional computing performance, but as the highest-end option on every axis simultaneously. The first laptops and desktops powered by RTX Spark will come from Microsoft Surface, Dell, HP, Lenovo, Asus, and MSI, arriving in fall 2026. NVIDIA plans to release more than 30 laptop designs and 10 desktop configurations built around the chip. Segment 6, the industry earthquake in the PC market. When Jensen Huang said RTX Spark would reinvent the PC at Computex, he wasn't just using marketing language. He was describing what Wall Street instantly understood as a competitive earthquake. On the day of the announcement, while NVIDIA stock jumped more than 6%, the market handed out a very different verdict to the incumbents. AMD fell, Intel fell, Qualcomm fell. Dell jumped 10% because they're a launch partner. Microsoft rose. The stock market was collectively pricing in what analysts were saying out loud. NVIDIA is coming for the PC CPU market, and it's bringing the most formidable AI software and hardware stack in the industry with it. One key reason for this is the ARM architecture. For decades, the processors running Windows PCs used x86 instruction sets, pioneered by Intel in the 1970s and extended by AMD. ARM, the alternative architecture known for its power efficiency, went mainstream in consumer devices when Apple adopted it for the iPhone in 2007, and then made a landmark statement when Apple put it in MacBooks starting in 2020. Those Apple Silicon Macs dramatically outperformed and outlasted x86 laptops on performance per watt, and the industry took notice. NVIDIA had actually tried to buy ARM outright in 2020 in a $40 billion deal that regulators ultimately killed. It didn't need ARM's architecture to lose, though. The world moved to ARM anyway. And now NVIDIA is shipping its own custom ARM-based chip for PCs, developed in partnership with MediaTek of Taiwan using TSMC's 3-nanometer process, with the most powerful AI acceleration stack of any client device currently announced. Analyst Neil Shah of Counterpoint Research described the announcement as revolutionizing how PCs would look like in the next 10 years. The framing that resonated most was Huang's own, that this reinvention of the computer is as big a deal as the reinvention of the phone into the smartphone. That's a very specific historical reference. The iPhone didn't just add features to an existing phone, it replaced the entire product category with something architecturally different. If Huang's bet lands, the RTX Spark era PC does the same. Segment 7, the competitive landscape and the risks. None of this happens in a vacuum. NVIDIA's dominance in AI chips has become one of the defining business stories of the decade, and competitors have not been sitting still. AMD's latest MI400 series chips pack 320 billion transistors and are explicitly targeting the same hyperscaler customers NVIDIA serves. Google has its own in-house AI chip program, TPUs, and has been investing heavily in custom silicon for its data centers. Amazon has Trainium, Microsoft has Maya, Intel is pushing its Gaudi AI accelerator line, and has been making aggressive cost arguments against NVIDIA's pricing. The honest assessment is that none of those alternatives has managed to seriously dent NVIDIA's position so far. Part of that is hardware performance, but a bigger part is CUDA, NVIDIA's software ecosystem that has been in development since 2006 and has become the de facto programming language for GPU-accelerated computing. Every major AI framework, every research library, every production AI system in the world is built on CUDA. Switching off NVIDIA isn't just a hardware decision, it's a software migration that most companies aren't willing to take on when the alternative works and the cost of failure is high. On the RTX Spark side, the risk is different. ARM-based Windows PCs have been attempted before. Microsoft's own Surface X line used ARM chips from Qualcomm and ran into serious compatibility issues, with many Windows applications refusing to run natively. Qualcomm's Snapdragon X Elite has made progress on that front, but the Windows on ARM software ecosystem still isn't as seamless as x86. NVIDIA is betting that the combination of better performance and the gravity of an AI-native computing era will pull developers and software makers to optimize for ARM faster than they did before. It's a reasonable bet, but it's still a bet. There's also the power consumption question. The Vera Rubin NVL72 rack consumes an estimated power load equivalent to roughly 40 average American homes at full draw. Data center operators, considering upgrades to Rubin, need to think carefully about whether their facility's power delivery and cooling infrastructure can handle the upgrade. NVIDIA argues that the efficiency gains per computation more than offset the absolute power increase. But the absolute power draw is still a real constraint for deployment timelines. Segment 8. What this looks like in 5 years. Pull back for a moment and think about where all of this is pointing. At the data center level, Vera Rubin is already in production. The second half of 2026 will see it deployed at scale by AWS, Google Cloud, Microsoft Azure, and Oracle Cloud, followed by a broader rollout into enterprise and research environments. NVIDIA has already named what comes after Vera Rubin, a platform called Rubin Ultra, which will scale to racks of 576 GPUs, delivering 15 exaflops of compute, with up to 1 terabyte of HBM4E memory per GPU. And after that, a platform called Feynman, named for physicist Richard Feynman. The one-year cadence NVIDIA is maintaining makes it increasingly difficult for any competitor to catch up in absolute terms. By the time AMD or Google's custom silicon catches up to Vera Rubin in performance, NVIDIA will be 2 generations ahead. At the consumer level, if RTX Spark lands the way NVIDIA is betting, the implications ripple out to every app developer, every content creator, every gamer, and every enterprise that deploys PCs to its workforce. Running a powerful AI model locally, without cloud latency, without cloud costs, without an internet connection, changes what kinds of AI applications are practical to build. Agents that work on your files, your calendar, your emails, your screen, doing it all on your device without sending sensitive data to a server. That's the vision Huang put on stage at Computex, and RTX Spark is the hardware meant to make it real. The combination of an unassailable position at the top of the AI chip market and an aggressive new entry into the personal computing market is NVIDIA making a very specific argument that wherever AI compute happens, in a data center on the edge, in your hands, it should run on their silicon. 2 chips. One designed for a warehouse, one designed for your bag. Both of them built around the same central conviction that Jensen Huang has been quietly acting on for years, that computing, all computing, is converging toward AI. The Vera Rubin platform doesn't just make AI faster. At 10 times lower cost per token, it makes AI possible in places that were economically out of reach before. RTX Spark doesn't just make laptops more powerful. It moves an AI supercomputer from a monthly cloud bill to a device you own sitting on your desk. NVIDIA's critics will point out, correctly, that some of these numbers are marketing claims, that real-world benchmarks will tell a more nuanced story, and that the history of chip announcements is full of promised performance gaps that narrowed once independent labs got their hands on the hardware. All of that is fair, but consider where the company was standing when it made these announcements. Already the world's most valuable company, data center revenue growing every single quarter with no deceleration, Blackwell chips sold out months in advance with millions of units on back order. This wasn't a desperate move from an underdog trying to stay relevant. It was a company at the absolute top of its game, making a calculated bet that the next generation of computing belongs to them too. Whether RTX Spark reinvents the PC the way the iPhone reinvented the phone, only time will tell. But one thing is already certain. The AI era isn't coming. It's here. And NVIDIA just built the engine it's going to run on.